Now that we have a numerical solution to our boundary value problem, that is the governing equations and boundary conditions, let's consider how good the results are by undertaking verification and validation. We'll do verification here, and then in a later video, we will think about validation. And to think about what we need to do under verification, what are the kinds of things we can do, let me go to my slide. Okay, so, and to think about what we need to do for verification, I'll go back to the framework of what's inside the black box, and because it tells us, it indicates what we need to do under verification. And in fact, the verification builds on the pre-analysis. So I'm making two columns here. On the left of the pre-analysis are the pre-analysis steps, and on the right are the verification steps. So we'll go through each pre-analysis step and think about what is the corresponding verification step. The first thing we did in pre-analysis is think about the mathematical model. Okay, what is a mathematical model governing equations and boundary conditions? And what's the domain over which we solve the governing equations? So the corresponding verification is to check if the results are consistent with the mathematical model. So what we see here in the color pictures and other results, is it consistent with this mathematical model? For instance, is the boundary behavior consistent? So looking at the behavior of the solution, of the velocity, pressure, temperature at the boundaries, is that consistent with the boundary conditions in the mathematical model? For instance, one of the common mistakes is putting in the wrong boundary conditions into the solver. And there are other things one can check, and I'll list those out in the next slide. The second thing we considered in pre-analysis is how the tool, Fluent in our case, is solving that mathematical model through a numerical solution. So that was the second thing we looked at. And there are errors introduced in the process. So the corresponding verification check is, are the numerical errors introduced by the numerical solution procedure acceptable? Okay. And we'll look at the linearization and discretization errors. More on that on the next slide. And the third thing in the pre-analysis is to consider what kind of hand calculations one can do of the expected results and trends. By the way, the hand calculations can feed into verification, can also feed into validation if you're looking, if your expected trends are based on the physics of the problem. Or it's based on, other people's experimental correlations and so on. But some of it often feeds into verification. So the third thing to do is to, compare the results to the hand calcs. So whatever results you have, is that consistent with the hand calcs? So let's list out, in more detail what we need to do under 1 and 2, and I'll do that in the next slide. So, and that gives me a nice verification checklist. And I'll put the framework to the right, because this is how I'm organizing these ideas, this verification checklist in my mind. And otherwise it's just this, it's just like a recipe of checks that you can do. But if you have this kind of organization of what the solver is doing, then this verification checklist, makes a lot of sense. So in the first set of checks, are the CFD results consistent with the mathematical model? We'll check boundary conditions, including the sensitivity to, the K and epsilon at the boundary, which we really don't know. We want the results to be insensitive to that. We'll check material properties, particularly the density, if the density is consistent with what we expect it to be. And these are common mistakes I see students do, putting in the wrong boundary conditions, material properties, and so on, and check the coordinate system, that the solver is actually using the cylindrical coordinate system rather than the Cartesian. And the next set of checks would be checking mass, momentum, and energy conservation for the entire domain, because conservation is the key physical principle contained in the mathematical model. Mass is easy to do, and energy is easy to do, so we'll do both. Momentum, there's not an inbuilt way in Fluent to do that, so we won't do that over here. Check the density temperature coupling. We saw it's coupled through the ideal gas law, but with the change in density is only due to change in temperature, because the change in pressure, the absolute changes in pressure are pretty minimal. So we can do a quick check on that. Ideally, one would also check sensitivity to the turbulence model, because one of the a big set of assumptions in the mathematical model is the K epsilon turbulence model, because it's making a lot of guesses about how these fluctuating quantities are related to the mean quantities. We won't do that here, but it's a good practice when you're doing this in the real world to check the sensitivity to the turbulence model. And I've done cases where I have used I've switched from the K epsilon to the SST K omega. That's another popular turbulence model that Ansys usually recommends, and I've gotten quite different results. Okay, then the second set of checks, so that was the first set of checks. The second set of checks are the numerical errors. The linearization error, we'll check by monitoring imbalances. That's automatically reported, and we got them down to a level of 10 to the power of -6. And it's a good idea to check the drag coefficient too. More on that in a later video. And then we'll check the discretization error by refining the mesh, and I'll show you how to do that in an automated fashion. And then the third set of checks is the hand calcs, and I won't be going through that in much detail here, but it's something that is good to get into as a practice. Okay, so at this point, we can get into the first set of verification checks, which is whether the results are consistent, whether the CFD results are consistent with the mathematical model. Let's do that next.